Bismillahirrahmanirrahim. Okay, today is our lecture number 5, the reinforced concrete design, and we'll be discussing analysis and design of two-way slab system without beams, which include flat plates and flat slabs. There are two sessions in this lecture. In session 1, we will discuss flexural analysis and design of two-way slab system without beams, which is basically based on a method called as direct design method. And session 2 is on the shear design for two-way slab system without beams. So in the session 1, we will discuss the flexural analysis and design of a two-way slab system without beams. Okay. The topics to be addressed under this session include background of the method, introduction to direct design method, frame analysis steps using the direct design method. Then there is an example 1, and we have two-way slabs requirements of the ACI code, example 2, 3, and summary of the direct design method. The objectives of this lecture are, at the end of this lecture, the student will be able to analyze flat slabs and flat plates for flexure using direct design method, which is called as DDM shortly, and analyze and design flat slabs and flat plates for shear. This is the background. Okay, if you remember, in the previous several lectures before the midterm, we used to discuss any analysis and design of 90 by 60 feet hall, and we designed this in several ways as a one-way slab system, as shown in this option 1 and 2, and we also designed this 90 by 60 feet hall using two-way slab system by providing columns inside this hall, and this analysis and design was done using the moment coefficient method using the ACI code tables, if you remember. Okay, so in this system there were beams, so beams were included. Beams were running on the column center lines. If beams are removed from the system, still the system can be analyzed and designed, but then the system will be slab without beams, which can be provided or not. Okay, so in the same 100 by 60 feet commercial building, if there are shallow or no beams, if the depth is too small, and then the moment coefficient method cannot be used. We have discussed it, why moment coefficient method cannot be used, because there is a basic assumption in the application of moment coefficient method that beams must be stiff enough to resist the deflection of the slab at the point where the beams have been provided. If beams are not present, or if beams are very shallow, then the beam stiffness will not be such that it will succeed in preventing or resisting the deflection of the beam at those locations. So moment coefficient method will not be applicable under that condition. So if moment coefficient method is not applicable, you have seen that moment coefficient method application was very simple, and if beams are stiff enough, which is usually the case, then moment coefficient method can be very conveniently used. However, if there are no beams in the system, you must have seen slabs without beams, okay, which are not very common in the reinforced concrete frame structure, but still quite a good number of systems contain flat slabs and flat plates. Depending on the situation, it will depend on the situation. The situation will decide to use which type of frame system. Sometimes in high-rise buildings, it is important to accommodate more number of stories, because the financial feasibility of the project is also very, very important. It is the most important characteristic which will decide the future of the project. So in order to make more stories and earn more money and to make the project financially feasible, the clients would like to have flat plate system instead of slabs with beam system. Because if there are beams, if there are beams in the system, then the overall story height, which is called as the headroom, must be kept such that they accommodate the usual living conveniently. Which is the minimum standard for a headroom is 9 to 10 feet, clear 9 to 10 feet, okay, depending on the purpose of the building. So with 9 to 10 feet, if the drop of the beam is added, which is usually 1 feet to 1.5 feet, then the overall story height from center to center of the floor will be around 11.5 to 12.5 feet. And if beams are omitted completely, then around 1 feet story height can be reduced. So if 1 feet story height is reduced, then in a 10-story structure or 12-story structure, one complete story can be added in the same height, which will earn extra money and can make financial impact on the project. For this purpose, flat slabs and flat plates are used in most of the client investors and builders. They like the flat plate and flat system because if there are no beams, then they don't have problems of beams coming in rooms and bathrooms in other areas. However, there are disadvantages of flat plates and flat slabs as well. They are not good system as with regard to their resistance to earthquake forces. They are inferior to slab with beam system when we talk about the earthquake resistance of the system. And for this reason, flat plates and flat slab system are not recommended in zone 3 and 4 of the seismic hazards zones. They are allowed, however, in zone 2A and 2B. If they are used in zone 2A or 2B instead of slab without beams, then by and large, the slab with beam system will be economical as compared to slab without beams. Although the overall cost may not vary too much, because saving of one story in the structure and then saving of accompanying masonry and all other associated material involved in the every story will be saved, and ultimately it will depend on the situation that which system is economical. From the structural point of view, from the reinforcement and from the concrete material, the slab with beam system is generally the most economical system. However, if the situation is such that slab without beams are required, and if it is a demand from the client, then we would like to have the slab without beams in our system, especially if the structures are located in zone 2A and 2B. So this is the background of this system, and finally it will depend on many parameters. The final selection will be done after a lot of trials at which system is to be finally used. In Dubai and in Middle East countries, most of the Middle East countries, they prefer slab without beam system because most of the UAE countries, they are located in moderate to low seismic zones. So, and the land is very costly. So they like to have more stories. For this purpose, they prefer to omit beams in their frame system. Okay, in Pakistan, most of the reinforced concrete frame structures which have been built up to date. They are reinforced concrete frame structure with beams. But sometimes there is an urgency, and now with the increase in number of stories, I think in the future there'll be an increased number of people who will be using these flat plate system. Okay. If you have any question, you can stop me and ask your question. Just introduce yourself briefly. Just your name is enough, and you can ask a question. Okay. So this was about the system. Now, which method shall be used for the analysis and design of slabs without beams? If you remember, in the previous several lectures, you have seen that most of the time we are busy in analyzing the system instead of actually designing. And analysis is one of the most important steps in the overall design process. If you look at the overall design process, it includes, first of all, an assumption of our selection of the sizes of different members, like beams and slabs and columns. Okay, and then the calculation of loads is also very important. And third is the analysis. And fourth is the actual design steps in which we actually calculate reinforcement, which we call as design step. Though the overall 4 steps are the steps of design. So the third step, which is the step of analysis, is one of the most important steps. And you would have seen in the previous several lectures that the third step is the most crucial step, because it involves the analysis, and sometimes it is difficult for us to analyze a system using the exact method of analysis. And for this purpose, the ACI code allows us to use approximate method of analysis. Although all these approximate methods of analysis are actually an alternate choice instead of the exact method of analysis. Okay. So if you have an access to computer and you can use a computer software easily, software is available, and and if you know how to analyze a system, you are allowed to analyze system using the computer software based on the finite element analysis, other techniques. The most famous software are SAP 2000, ETADS, Stat Pro, and all these software are very frequently used by structural engineers. Okay, however, the ACI code permits us to use alternate methods of analysis. Okay, and these alternate methods of analysis must be recognized by the ACI code. The ACI code would allows you to use they would allow you to use a certain method, and they can also stop you from using other methods. So over the course of time, the ACI code has abandoned some methods, they have stopped using some methods, and they recommended some other methods. Okay, the DDM method was also one of the famous methods of analysis for flat plates and flat slabs, especially. But in the most recent code, this method has also been abandoned, and this has been removed from the code. The method of moment coefficient method, which we have used for slab with beams. If you remember, we have also clarified that this method also no more exists in the current versions of the ACI code. The DDM was part of the code until 2014, but in the most recent version of the code, this method has not been included. But still, the ACI code allows us to use the method. Okay, because this method is very useful for slabs without beams. Okay, for slab with beams, the method is very laborious. So for this reason, we have included in our lectures moment coefficient method for slab with beams and direct design method for slab without beams. The name direct design method shall not be confused with the word design. Direct design method is basically a method of analysis. It's not a method of design. And because analysis is one of the most important steps of the overall design process, for this reason, the method is called as direct design method, although it is a method of analysis and a method of flexure analysis, not of shear analysis. Okay, so this should be very clear to you. Okay, so now we will discuss this method, direct design method, by discussing the steps of the method. Okay, the first difference in the DDM, the first difference between the DDM and the moment coefficient method is that in the moment coefficient method, if you remember, we analyzed panel by panel analysis was done in the moment coefficient method. One panel which was continuous or not continuous, and then there were tables, and we used to pick up values from the table, inserted the values in the relevant equation, and calculated the bending moments. In the direct design method, the frames are analyzed instead of panels, as you will see in several upcoming animations. For example, if we want to analyze this system, this slab, if you want to analyze using direct design method, the center lines are the dotted lines which run on the column center line. They are just center lines. They are not beams. Okay, so the system does not contain any beam. First of all, we will divide the system into frames. Okay, this one of the frames that you can see now on the screen is an interior frame. This is an interior frame. So interior frame will be marked, and the frames will be analyzed one by one in both directions in order to get the bending moments in the slabs. Then there is an exterior frame, another frame, and another frame. Interior frame, two interior frames and one exterior frame, if they are analyzed like a beam, this analysis will be done like a beam with this width. This will be analyzed along this length, along the length of the frame. This is the width of the frame. Okay. Then the frames along the
excuse me, sir,
direction will also be analyzed. Okay. After the analysis is completed along both the directions, then the design will be done for the relevant bending moments. Okay. The limitations of the method. Because direct design method is an approximate method of analysis, every approximate method has its own limitations, and so are the limitations of direct design method. Though DDM is useful for analysis of slabs, especially without beams, the method is applicable with some limitations as discussed next. Okay, these are the limitations. The first limitation of the method is that the live to dead load ratio shall be less than or equal to 2, which means that live load shall not be very high as compared to dead load. Okay, usually dead load is more than the live load. Okay, so this method is based on an assumption that live load to dead load ratio shall be less than or equal to 2. If it is more than 2, then this method will not be applicable. And these are discussed, these limitations have been discussed under the section ACI 8.10.2 of the ACI 1814. Okay, and the length of the length of spans, the span length shall not vary by more than 67%. So, which means that if this length L1, if this is L1, then L2, the length of this adjacent panel shall be more than or equal to 67% of this at least. If it is less than this, which means that the difference cannot be more than 33%. If the difference between the adjacent span is more than 33%, then the method will not be applicable. Okay, another limitation, which is one of the most strict limitation, which restrict the use of this method, is the number of panels. If the number of panels in each direction shall be 3 or more. So this is one panel, another panel, another panel. Okay. So if there are 3 or more spans in both directions, both orthogonal directions, then the method will be applicable. However, if there are only 2 panels along one direction and 3 or more spans along the other direction, then the method will not be applicable. So it is one of the most strict limitation of this method, and which limits the use of DDM. Okay. Then the panel must be rectangular or square. Okay, and the ratio of long to short side shall not be more than 2. The ratio shall be 2 or less. Okay, the ratio of long to short side shall be 2 or less, which will make this behavior like a two-way slab behavior. Okay, that the bending moment along both directions will be there, and both shall be calculated. Okay, and the column must be placed on, all the columns must be placed on a common center line. However, if one of the column offsets from the main center line, the offset shall not be more than 10% of the width of the panel. If this is the width of the panel, then this column, if this column is out of the column center line, main column center line, then it shall not be more than 10%. Okay, so these are the limitations. Next, the sizes to be selected in the direct design method. They are different than the sizes selection which we have used in the slabs with beams.
Excuse me, sir.
Ji? Please. Any question?
Sir, span should be more than 3 or more in both direction or in one direction.
Both directions. Which means 3 panels in one direction, 3 panels in the other direction. At least. If there are more, it's okay. Okay. Initially, we can use this table for the selection of thickness of the slab, because there are no beams in the system. So there will be only thickness of the slab, and the slab must be thick enough now. So for this reason, the selection of the slab thicknesses are based on this table if the system does not contain any beam. Okay. There are basically 2 main columns. This column is without drop panels, and this column is with drop panels. You know what is a drop panel. We will discuss this in the next several slides. A drop panel is basically a thick part of the slab in the vicinity of the column, which drops below the main slab. So if it is without drop panels, which means there are no drop panels in that, it is a flat slab system. So if the panel is then exterior panel or interior panel, if the panel is exterior panel, then whether there are edge beams or not, sometimes beams run on the exterior edge of the overall frame, which stiffen the system and reduce its drifts in the high-rise building. So if it contains some edge beams at the periphery of the building, then this will be the formula or the equation for the initial thickness of the slab. Or if there are no edge beams, then this will be used. For interior panel, this will be used. Mostly we use this ln by this first column. First column we mostly use, regardless of whether there are edge beams or not, because we want to keep our thicknesses slightly on the higher side. Although from academic point of view, you should always use the correct way, the correct equation. From the academic point of view, you should use the correct equation. However, in our design practice, we mostly use this first column for the initial selection of slab thickness. Okay. If then you have a grade 40 steel, it will be ln by 33. If it is grade 60 steel, it is ln by 30, which means that if the length of the panel is 30 feet, then 30 by 30, you would require minimum 1 foot or 12-inch slab, thick slab. Okay, and so on. You can use the rest of the table. The minimum thickness, however, for slab without beams and without drop panel is 5 inches, and slab with drop panel is 4 inches. Factored load can be calculated in the usual manner. You know how to calculate this. Next is the analysis, and basically in the DDM, it is a new step for you in the design. Once the analysis is done, then the design for slab will be done in the usual manner. Okay, so you should pay attention to this step number 3, which is the main step of this lecture, or the DDM method. Okay, the first step, which we call as step 1A, sub-step A, is marking of the frame and marking of east-west interior frame. So we will do it like this. We will mark the column center line. Okay, the column center line will be marked in this manner. You can see in the animation the yellow dotted line, dashed line. Then we will draw another line on one of the sides of the column center line, and this line will be drawn or marked on the panel center. So this will be called as panel center line. Okay, on the panel center line on one of the on one side of the column center line. Similarly, another line will also be marked on the other side of the column center line, and then this will make an east-west interior frame. So this whole frame, east-west interior frame, will be analyzed. Okay, and this is the first step, but the marking of the frames is the first step of this overall analysis method, DDM method. This is the interior frame, half width of the panel on one side of the column center line and half width of the panel on the other side of the column center line. Okay, L2 is now width of this frame. L2 is width of the frame, and L1 is the design length of this frame. Okay, L1 is the design length of the frame. Every panel length will be L1. Okay, this L1. One, you will see this. What does it mean actually? According to ACI, where the transverse panels on either side of center line of support varies, L2 shall be taken as the average of adjacent transverse panel. So this is very obvious that if you look at this slab panel, this slab panel is 20 feet long, and the other slab panel is also 20 feet long, and the other panel is also 20 feet long. So all panels are having same length. Okay, so in this case, half of 20 is 10 feet. So from one side of this column center line, we will mark this red line a distance of 10 feet on this side, and also a distance of 10 feet on this, which will make the overall width of the frame is 20 feet. L2 will be equal to 20 feet. However, if there is a difference in the panel sizes, okay, then the average of the two will be taken as L2, which means that, for example, if this is 20 feet and let's say this is 24 feet, and the other side is 24 feet. So from this column center line, we will mark this line at 10 feet, and from this column center line, we mark this as 8 feet, 12 feet, sorry. So 12 feet plus 10, L2 will be equal to 22. Okay. In other words, 20 and 24, add 20 plus 24 and divide by 2. So this will also give you 22. Okay. So this means that if slab panels are not same in size, then the average of adjacent transverse span will be taken as L2. Then we will mark east-west exterior frame. And since in the exterior frame, the panel extends only on one side of the column central line, the yellow line. So we will consider only one side of this frame, okay, and this will be the case of the exterior frame. However, some small part of slab also extends to the column edge, to the exterior column edge, which will be shown in the next animation like this. So the total panel is basically the column central line plus half width of the panel, and then the small part of the slab which extends to the column edge. Okay, any part of the slab which extends beyond this column will not be part of this frame. That will be treated separately as cantilever slab. So the total width of the frame in this case will be equal to half the panel width on one side of the column central line plus half of the column size, because this is only half of the column. The slab extends only half the column size on the other side. So L2 in this case will be equal to panel width divided by 2. This is panel width is 20 feet, so this will be 20 divided by 2, 10 feet, plus H2 divided by 2. H2 is the column size in this direction, divided by 2. It's very obvious. This is how we mark an exterior frame. Then in interior frame, okay, next is the marking of column strip and middle strip. Okay, a column strip is a strip which is very close to the column central line. Okay, and the marking of column strip will be done in this manner. The column strip is defined as a strip having half of the column strip on one side and half of the column strip on the other side will be marked. And half of the column strip on one side of the column center line is defined as this. This is least of L1 by 4 or L2 by 4. L1 is this length along the frame, and L2 is the width of the frame. L2 is width of the frame, and L1 is the length of panel along the length of the frame. So least of L1 by 4 or L2 by 4 will be half column strip. For example, in this particular case, along the frame, the span length of all panels are same, 25, 25. So L1 is 25 and L2, which is the width of the frame, is 20 feet. So L2 is less than L1. Least of L1 by 4 or L2 by 4 means that 25 by 4 or 20 by 4. So obviously 20 by 4 will be less. 20 by 4 is 5 feet, which means that half of the column strip on one side of the column central line is 5 feet, and on the other side is also 5 feet, because all panels are equal in size. So this total column strip marked is marked with the green color. This green color total strip is column strip, and this width of the total column strip is now 10 feet. Okay, 5 feet on the other side and 5 feet on the other side. 5 feet on one side and 5 on the other side. The remaining strip on both sides of the frame from the column central line will be called as middle strip, half middle strip. So if you look at this arrow, yellow arrow, this part is half middle strip. This is half middle strip, and this is half middle strip of the frame. Okay, middle strip divided by 2 means half middle strip. And this is total column strip. This is total column strip. Why do we need to divide the frame into column strip and middle strip? The reason being that the column strip would attract more bending moment because it contains columns along this line. So they are much stiffer than the remaining part of the slab. As you will see in the coming slides, that once we calculate the overall bending moment, so most of the bending moment will be taken by this column strip. So for this reason, column strip and middle strip marking is important. This is just to calculate the column strip calculations. Okay, 5 feet, 5 feet. The total column strip is 10 feet. 10 feet column strip. And 5 feet middle strip, half middle strip on one side and 5 on the other side. This is just a demonstration of the previous step. Demonstration of the previous step. Nothing new, okay? Now marking column strip for exterior frame. Column strip for exterior frame is minimum panel width divided by 4, because column strip only extends on one side of the column center line. So this will be calculated like this. Okay, the column strip on the other side will be equal to from the column center line, half of the column will be added to this column strip. So column strip on one side, on the interior side of the frame, will be minimum panel width divided by 4. Minimum panel width divided by 4. So 25 feet and 20 feet. Out of 25, 20 feet, 20 is minimum. 20 divided by 4 is 5 feet. Okay, as you will see, like this. Column strip is 20 divided by 4 plus half of the column size. The column size in this case is 14 by 14 inch. So 14 divided by 2 is the column strip in this case. And total L2. L2 is calculated as half of the panel, with 20 divided by 2. 20 divided by 2 is 10, and plus half of the column size on the other side of in the exterior side of the column central line. So L2 is 10.5 feet. 20 divided by 2 plus half the column size, 10.5 feet. Column strip is 20 divided by 4 plus half this 5.5 feet, and the remaining is middle strip. This will be middle strip. The middle strip will be L2 minus column strip. This will be middle strip. Next is to calculate bending moments now within the frame. So remember that in every span, the total bending moment called as statical moment, m naught, will always be equal to W2 ln square divided by 8. For example, if you want to calculate bending moments in this yellow part of this frame, yellow part, which is one of the interior spans of this frame, then the total bending moment m naught will be equal to WU L2 ln square divided by 8 m naught. Okay, total static moment. L2 is width of the frame, and ln is the clear length of this frame. Okay, and WU is load per square foot of the frame. Okay, so the bending moments are basically calculated in a manner similar to the bending moment calculation of a beam. When L2 is multiplied with WU, it basically calculates the load per running foot, and then ln square by 8 will give us bending moment in the total width of the span, interior span. Once this bending moment is calculated, further this bending moment is distributed along the length. This is along the length of the frame, along the length of this span, into negative bending moment and positive bending moment. Because you know that we have negative bending moments at the supports and positive bending moments at the mid span. So the negative bending moment value is 0.65 m naught, and the positive bending moment value is 0.35 m naught. Okay, so it will be it is called as longitudinal distribution of the bending moments of the m naught. Once this is done, then we laterally distribute the bending moment into column and middle strip like this. Okay, the column strip out of this total bending moment in the negative part, this part, which was m naught, it was m negative 0.65 m naught and m positive 0.35 m naught. Out of this total bending moment 0.65 m naught. Now 0.75 of this, 0.75 of this will be taken by the column strip, and the remaining 0.25 will be divided into two parts, half the middle strip on one side and half the middle strip on the other side. Okay, the positive bending moment 0.35 m naught, this 0.35 m naught will be multiplied by 0.6. So 60% of the total positive bending moment will be given to column strip, and the remaining 20% will be distributed, will be divided in the two middle strip on both sides of the column center line. On the other side, the column, the bending moment distribution is the same. Okay, so now coming to the exterior span, one of the exterior span of the frame. In the exterior span of the frame, the total bending moment remains the same, WU L2 ln square divided by 8. However, the distribution, longitudinal distribution, will be different. Okay, in the exterior span, the distribution will depend on the end conditions. If the end conditions are such as shown in this slide, without beams, no beams, then the distribution will be such that the negative bending moment, exterior negative bending moment, will be 0.26 m naught, and the interior negative bending moment will be 0.7 m naught instead of 0.75 m naught. And the interior, in the positive bending moment, will be 0.52 m naught instead of 0.35 m naught. Okay. And if we now laterally distribute this bending moment, so 100% of the bending moment of this will be given to the column strip, and 60% of this positive bending moment will be taken by the middle strip, and the remaining 20 will be given to the middle strips. The 60% will be given to the column strips, and the 0.7 of this m naught, 0.75 of this, 75% of the bending moment will be taken by the column strip of this value. Okay, so if you want to write this in one slide, the slide number 27, I would ask you to write down in your notes. This is one of the most important slides. If you remember this slide number 27, you can analyze the system, because all the relevant questions are given in this slide. I will just quickly repeat the method. In this method, you have seen that we first of all mark the frames, interior frame, exterior frame, in the north, south, and east, west direction. And then in the interior or exterior steps, we further mark the column strips and middle strips. Once the column strip and middle strips are found out, then the statical bending moment in the interior and the exterior span are calculated from the equation WU L2 ln square divided by 8. And once this is done for any span, these are the questions to be used. For the exterior, this whole bending moment, this is 0.26 m naught. Out of this 0.26 m naught, 100% will be given to column strips, nothing to the middle strip, 0, 0. Okay, and this 0.52 m naught, which is the total bending moment in this part, 60% will be given to the column strip, positive bending moment, and 20% of this 0.52, 20% will be given to the middle strips. This 0.7 m naught is the total bending moment here, 0.7 m naught. Out of this 0.7 m naught, 75% will be taken by the column strip, and the remaining 12.5 and 12.5 will be taken by the middle strip. Okay. In the interior spans, all the interior spans will be similar. This will be similar. This will be similar to this exterior span, and no matter how many spans are there, all the interior spans will carry same coefficients. Okay, this 0.65 m naught is the total bending moment here. 0.65 m naught. Out of the 0.65 m naught mean m naught is WU L2 ln square divided by 8. And 75% of this 0.65 m naught will be taken by the column strip here, and the remaining 12.5 will be given to this. And similarly, 0.35 m naught is total bending moment here, total 0.35 m naught, out of which 65% will be taken by column strip and 20 will be taken by middle strips, and so on. So you should write down now this slide in your the coefficients, the relevant coefficients. All the relevant coefficients are available on this slide number 27. So you better write down these coefficients in your notes, and then also try to analyze and find out the bending moments using these coefficients for the given system. You know that the given system is 25 by 20 feet. Okay, you assume any data. Okay, our next, okay, you write down these coefficients, and next I will give you the data, and you can practice yourself and find out the bend moments, and then we can compare with our values. So it will develop your confidence in the method. Okay, and after you practice this, if you have any question, we will give you some time for your questions. So you write down these questions in your notes, and then we will continue. Okay, just 5 minutes.
अगर आपका कोई क्वेश्चन हो तो आप पूछ सकते हैं.
Yes, sir.
Okay, Ahmed.
Yes, sir. We have actually five moments which is given for static moments,
Okay.
but the strips, the interior and exterior, they are divided into six. Yes.
Which one panel you are talking about?
I'm talking about the interior strips.
This is the interior.
Yes. So if you count from the beginning, the first moment for exterior has been divided for the mid strip 100%.
For exterior, we will divide 100% exterior negative bending moment, and this is the exterior negative bending moment 0.26, 26% of m naught of the whole bending moment will goes to this exterior portion.
Okay.
This exterior portion, and of this exterior portion, exterior negative bending moment, 100% will goes to column strip, and 0% will goes to middle strip.
This for positive or negative?
This is for negative, for minus negative
Positive,
bending
right?
moment, and for positive bending moment, the 60% will goes to the column strip.
Okay.
60% of this exterior,
Okay.
60% of this 0.52 m naught.
Okay.
When
What
you
about
find when you find out m naught, the whole bending moment, then multiply 0.2, 0.52, 52% of m naught will goes to this positive bending moment, and of this exterior positive bending moment, 60% will goes to the column strip.
okay? For the coming
Got it,
for
Ahmed?
the yeah, I got it for exterior. What
Have you
about
got it this point?
exterior? Yes, I got it for exterior.
Okay.
What about the interior, sir? Just my question is for the interior. Which moment do you use?
For interior positive bending moment, also 60% of this 35%, 35% of m naught will goes to this region. 35% of m naught. When you find out m naught, then 35% will goes to this region, this positive bending moment, and from that m positive, 60% will goes to the column strip.
Okay, and the end, the middle one, which is been divided 70%, 75% for each, positive and negative. The mid one, the yellow color. Yes, this one.
This one, are you talking about this one?
Yes.
You will find out the 75% of exterior negative, exterior.
Is this
26%, when you find out 26% of m naught, then 75% will goes to the column strip from this
okay?
from this value.
Okay. For the and what about the next portion of the same strip?
On this side, you will
Yes.
you will take the 75% of this 65% of m naught. When you find out m naught, then multiply 0.65 and then multiply 0.75. Then you will take this column strip bending moment.
Okay, okay. I understand now.
सर
Thank you.
जी जी
सर ये हमने जो ये पैनल को थ्री पोर्शन में डिवाइड किए, दो नेगेटिव और एक पॉजिटिव, तो सर ये इक्वली डिवाइड किया हमने।
हाँ इक्वली डिवाइड किया है।
और सर इसमें जो ये लोड होगा ये येलो पोर्शन का, सर ये बिल्कुल ये रेड पैनल जो सारा होगा ये सारे पे जाएगा कि नहीं सर? सिर्फ ये येलो जो शेडेड है इधर होगा ये लोड।
आपकी बात समझ नहीं आ रही थी।
सर ये नेगेटिव मूवमेंट नहीं है सर, ये जो येलो कलर है, ये येलो जो
जी जी
शेडेड एरिया है,
जी
तो
जी
ये लोड नेगेटिव सिर्फ इधर ही होगा कि नहीं सर? ये जो रेड बाउंड्री डिमार्केशन की इधर तक जाएगा ये लोड?
नहीं, बिल्कुल इधर ही तक होगा ना। ये अप्रॉक्सीमेट मेथड है ना, इधर तक हम एज्यूम करते हैं कि इधर तक किया जाएगा, ये बिल्कुल इस रीजन तक। फिर इसके बाद ये मतलब अगर आप फाइनाइट एलिमेंट सॉफ्टवेयर से ये करें तो फिर ये मतलब जीरो वैल्यू यहाँ पे दे देगा। इसके बाद डिक्रीजिंग जीरो वैल्यू स्टार्ट होगी ना यहाँ पे। ये तो अप्रॉक्सीमेट मेथड है ना।
तो ये लोड सिर्फ येलो येलो रीजन में लोड जो अलाई करेगा?
हाँ बिल्कुल येलो तक, ये यहाँ पे ये सारा बेंडिंग मोमेंट इस रीजन पे आएगा।
सही है।
यहाँ पे 100% इस रीजन में होगा।
सर
जी
सर ये एक्सटीरियर मूवमेंट पॉजिटिव, एक्सटीरियर मूवमेंट नेगेटिव और ये इंटीरियर मूवमेंट नेगेटिव है, उनका सम 100% के बराबर नहीं होना चाहिए।
किसकी बात करते हैं?
ये पहले सर 26 और 50, 52 और 70 जो है।
जी इसकी बात करते हैं।
जी जी एक्सटीरियर के लिए सर।
हाँ एक्सटीरियर।
उनका अगर हम सबको ऐड अप कर लें तो फिर 100% मूवमेंट होना चाहिए ना सर? जिस तरह ये नीचे है सर 65 और 35 तो 100% मूवमेंट आता है सर।
अच्छा जी, क्वेश्चन कौन क्वेश्चन कर रहे हैं? क्या क्वेश्चन है? आप क्वेश्चन दोबारा करें।
सर जी ये इंटीरियर पैनल जो है
आप
इसके
कौन
लिए
बात
ये
कर रहे हैं?
नेगेटिव मूवमेंट। सर आसिम हसन सर।
आसिम, चलो जी बात करें आप।
सर जी ये इंटीरियर पैनल के लिए सर ये नेगेटिव मूवमेंट और पॉजिटिव मूवमेंट जो है सर उनका जो सम अप हम कर लें तो सर 100% मूवमेंट आता है 65 और 35 का, लेकिन एक्सटीरियर मूवमेंट के लिए ऐसा नहीं आता सर, ये क्यों सर?
अच्छा, ये 0.26 और 0.7 आप दोनों जमा करें।
0.26, 0.7
इसको 2 पे डिवाइड करें।
कर लिया सर।
अच्छा, आप जमा
48
करो 0.52 के साथ।
यस सर, अब आता है सर।
आ गया? अब आप खुश हो गए?
यस सर, यस सर।
एक्सक्यूज मी सर।
जी जी
थैंक
भाई।
यू सर।
सर जकरिया सर, ये थोड़ा सा प्लीज दोबारा सर एक्सप्लेन करें, ये स्लाइड की समझ ज्यादा नहीं आई सर।
अच्छा अच्छा, ये असल में इस तरह है कि ये बात आप लोग याद रखें कि किसी भी स्पेन के अंदर कोई भी स्पेन हो ना, स्पेन कहते हैं बिटवीन द कॉलम्स। जब आपका कोई स्लैब पैनल होता है उसको हम एक स्पेन कहते हैं ना, ठीक है। जिस तरह कि आपको इसमें एक एक्सटीरियर स्पेन है, एक इंटीरियर स्पेन है, तो इसमें बीम्स हो या न हो, लेकिन इसमें हमेशा बेंड मोमेंट की टोटल वैल्यू WL²/8 के बराबर होगी। आप लोगों ने बीम के एनालिसिस काफी दफा किए हुए हैं ना, तो अगर आप सपोर्ट टू सपोर्ट किसी बीम का पोर्शन देख लें अपने एनालिसिस के नोट्स में, और उसमें आपके पास 2 नेगेटिव बेंडिंग मोमेंट्स होंगे, इंटीरियर पैनल की बात कर रहा हूं, और एक पॉजिटिव बेंडिंग मोमेंट होगा। अगर आप उनको जमा कर लें तो आपके पास टोटल बेंडिंग मोमेंट हमेशा WL²/8 के बराबर आना चाहिए, ठीक है, क्योंकि टोटल बेंडिंग मोमेंट हमेशा WL²/8 के बराबर होता है। WL²/8 में दोनों एंड्स पे बेंडिंग मोमेंट 0 होता है, नेगेटिव बेंडिंग मोमेंट, सिर्फ पॉजिटिव बेंडिंग मोमेंट होता है ना। आपको पता है कि WL² सिंपली सपोर्टेड बीम के लिए इक्वेशन है, एग्जैक्ट इक्वेशन फॉर द एनालिसिस, ठीक है ना। तो उसमें हमारे पास चूंकि ये मैं आपको थोड़ा सा एक्सप्लेन कर दूं, ये इंटरेस्टिंग चीज़ है। ये देखिए, अगर आपके पास कोई कंटिन्यूस बीम हो ना इस तरह से, और आपके पास इधर मुख्तलिफ सपोर्ट्स हों, तो आप लोगों ने इस किस्म के तो बहुत सारे एग्जाम्पल आपने किए हुए हैं। इसके ऊपर यूडीएल है, तो इसका बेंडिंग मोमेंट डायग्राम कैसे बनेगा, इसका बेंडिंग मोमेंट डायग्राम ऐसे बनेगा, और ऐसे। अब ये जो मैं बात कर रहा हूँ सिंपली सपोर्टेड बीम्स की, कि उसमें ऐसे सिंपली सपोर्टेड बीम के पास है और इस पर यूडीएल है, तो इस पे आपका बेंडिंग मोमेंट हमेशा ये W²/8 के बराबर होगा, क्योंकि इधर 0 बेंडिंग मोमेंट है, ये W²/8 ठीक है। अब ये W²/8 है और ये बेंडिंग मोमेंट चेंज हो गया। तो ये क्यों चेंज हो गया? क्योंकि नेगेटिव बेंडिंग मोमेंट इधर आ गया, नेगेटिव बेंडिंग मोमेंट, तो इस नेगेटिव बेंडिंग मोमेंट ने पॉजिटिव को कम कर दिया। ये टोटल बेंडिंग मोमेंट W²/8 के बराबर था, लेकिन चूंकि नेगेटिव आ गया तो W²/8 कम हो गया, ठीक है। अब आप किसी भी इंटीरियर को, यानी इस पैनल को अगर आप ले लें, इसको अगर आप ले लें, तो इसमें एक इधर नेगेटिव बेंडिंग मोमेंट है, एक इधर नेगेटिव बेंडिंग मोमेंट है और एक पॉजिटिव बेंडिंग मोमेंट है, ठीक है। अगर आप इन दोनों नेगेटिव बेंडिंग मोमेंट को जमा करके 2 पे डिवाइड करें, एवरेज नेगेटिव बेंडिंग मोमेंट, और पॉजिटिव के साथ इसको ऐड करें, तो इसकी वैल्यू भी W²/8 के बराबर आनी चाहिए, होगी, जरूर होगी। अच्छा, इस केस में क्या होगा? इस केस में सिर्फ इधर 0 है और इधर नेगेटिव है, तो ये 0 प्लस नेगेटिव डिवाइड बाई 2, ठीक है, और ये पॉजिटिव बेंडिंग मोमेंट, इसको आप जमा करेंगे तो ये भी W²/8 होगा। अगर ये बेंडिंग मोमेंट 0 हो जाए तो 0 प्लस 0, यानी कि टोटल पॉजिटिव बेंडिंग मोमेंट W²/8 के बराबर आना चाहिए। तो मतलब कहने का ये है कि एक स्पेन में टोटल बेंडिंग मोमेंट की वैल्यू हमेशा W²/8 होगी। जब वो नेगेटिव और पॉजिटिव में डिस्ट्रीब्यूट होती है, तो जाहिर है कि पॉजिटिव बेंडिंग मोमेंट की वैल्यू जो पहले W²/8 थी वो कम हो जाएगी, और जितनी वो कम होगी उतनी नेगेटिव में चली जाएगी, ठीक है। आई होप दिस इज क्लियर नाउ। कुछ समझ गए आप लोग? आसिम, किसने क्वेश्चन किया था?
यस सर, मैं समझ गया।
क्वेश्चन किसने किया था? ठीक है जी। तो इस केस में एक्सटीरियर में 0.26 और 0.7 जो है, इसको अगर आप जमा करके 2 पे डिवाइड करें, फिर 0.52 के साथ जमा कर, तो फिर भी 100% यानी W²/8 का आएगा। अच्छा, नेक्स्ट वी विल अप्लाई दिस इक्वेशंस नाउ। दिस इज द केस ऑफ फ्लैट प्लेट, and you are required to analyze the flat plate shown below using DDM. The slab supports a live load of 144 pound per square foot. All columns are 14 inch square. FC prime is 4 KSI and FY is 60 KSI. ठीक है जी। लाइव लोड 144 पाउंड पर स्क्वायर फुट दिया हुआ है, विच इज वेरी अनयूजुअल। आमतौर पे लाइव लोड इतना ज्यादा नहीं होता, लाइव लोड 60-70 इतना होता है, लेकिन इस एग्जाम्पल में डिलिबरेटली हमने 144 पाउंड पर स्क्वायर फुट रखा हुआ है। और द रीजन इज दैट द सेम क्वेश्चन हैज आल्सो बीन सॉल्व्ड इन द नेल्सन बुक। सो हम उसको वेरीफाई करना चाहते थे कि उनके और हमारे जो आंसर्स हैं वो सेम आते हैं या नहीं। तो बेसिकली दिस इज ए क्वेश्चन फ्रॉम द नेल्सन बुक। तो आप देख लें, इसका 144 पाउंड पर स्क्वायर फुट लाइव लोड है, आप इसके डायमेंशन नोट करें। नेक्स्ट इसके लोड्स तक मैं करूंगा आपके साथ, फिर आप मूवमेंट खुद मालूम करेंगे। ओके, सो यू शुड पे अटेंशन टू दिस नाउ। The first step is the selection of size, and if you remember, I told you that we will mainly select ln by 30 as our initial value for our initial equation for the selection of thickness. For grade 60 steel, ln by 30, and okay, the slab panel is 25 by 20 feet. Okay, and we are, if you look at this slab, we are designing, let's say, this frame. So the length is 25 feet and the width is 20 feet. So you will be considering 25 feet, not 20 feet for the selection of size. However, if you are considering in the other direction, then you can take L as 20 feet. However, since regardless of the analysis of the frame in one or both directions, the slab is the same. So usually you will consider the slab thickness as uniform in all the panels, and it will be calculated based on the maximum length, which is 25 feet in this case. So 25 feet, 25 feet for 25 feet, we'll calculate the ln. Okay, ln is 25 feet, center to center, and the column size is 14 inch. So we will deduct this column size on both sides. 2 into 14 divided by 2, which means 1 column size. This 2 will be cancelled with this. So half of the column on one side and half of the other side, which means 14, and divide by 12 to convert this into feet, and then divide by 30, which is ln by 30. So this will give us initial estimate of 9.53 inch thickness according to the ACI requirement. Let's say we decide to round up this value to 10 inch. So initial thickness that we take is 10 inch. Okay. In the 10 inch thickness, we will also now select effective D. Effective D will be selected based on this figure. You know that total thickness is 10 feet. One of the other cover is 3 by 4 inch in slabs, so 0.75 inch. Let's say the reinforcement in one direction is also 3 by 4, in the other also 3 by 4. So one complete bar will be added to this, okay, to give us this D, effective average D for both directions. This will be effective average D for both directions. If this is the total thickness of the slab, then 0.75 inch one will be deducted, and 0.75 inch one complete diameter of this bar will be deducted from this. This will give us effective D. 0.75 minus 0.75. So 10 minus 1.5 will give you 8.5 inch effective D for both, assuming that we will be using number 6 bar in the slab. Service dead load. Service dead load. There is no superimposed dead load given in the example. The service dead load consists only of the slab load itself, which is 10 inch. 10 divided by 2 into 0.154, it is 0.125 kg per square foot. Service live load is 144 pound per square foot, 0.144 kg per square foot. Factored load 1.2D plus 1.6 L is 0.3804 kg per square foot is the ultimate load for which we should design, analyze and design this slab. The next steps I would ask you to do yourself. You will compare your values with ours, and I will give you now a 10 minutes break. In this break, to calculate the bending, first of all, follow the steps that we have seen in the previous slides. Okay, mark the column, mark the interior frame, then the column strip and middle strip, then use the relevant coefficients, and the WU is there with you, 0.3804 kg per square foot. Now you can use the statical moment, then the distribution of the values, and I hope you can do this very easily. You do this in 10 minutes, and then we will discuss and go ahead further. Okay.
ये क्लियर हो गया? You can compare your values with this values. आपने जो कैलकुलेशन किए वो इसके साथ कंपेयर करें, इन वैल्यूज के साथ।
सही आ रही है सर, कैलकुलेशन सही आ रही है।
ठीक, अब ये मिडल स्ट्रिप के लिए आप लोगों ने कैलकुलेशन किए, जो इससे रिमेनिंग आ जाए कॉलम स्ट्रिप से वो फिर 2 पे डिवाइड करके मिडल स्ट्रिप के लिए भी कैलकुलेट कर सकते हैं। अच्छा, जो एक्सटीरियर फ्रेम है ईस्ट वेस्ट, इसके लिए भी करें एक्सटीरियर फ्रेम।
एक्सक्यूज मी सर।
जी जी बताइए।
सर ये एक्सटीरियर ये मिडिल सेक्शन के लिए इधर सर तो उसने 112 डिवाइड बाई 2 लिया है ना, लेकिन हमारे साथ तो 113 डिवाइड बाई 2 आता है, क्योंकि 281 माइनस 168 तो इससे 113 आता है। मिडिल मिडिल
Okay. What is the problem?
मिडिल स्टीरियर सर स्टाइल ले आ जाए।
मिड स्ट्रिप में क्या चीज है?
सर इसमें हमने जो फाइंड किया है ना कॉलम स्ट्रिप के लिए वो 168 आता है ना।
168 पूरा?
ये सर और जो रिमेनिंग जो मतलब ओवरऑल इस फ्रेम के लिए था वो तो 281 आता है ना, तो 281 से जब हम माइनस करेंगे 168 तो इससे 113 आता है।
112 चलो खैर है, ये इतनी बात नहीं, हम चेक कर लेंगे, देख लेंगे। आप भी चेक कर ले, हम भी चेक कर लेते हैं, ठीक है?
ओके सर।
So we will now move ahead, okay? अच्छा, इसमें the last step in this analysis is that we will divide the bending moments we will divide the bending all the bending moments that you calculated in the total strip by the strip width, okay? For example, this 140 bending moment is basically, this is the absolute bending moment in the total strip. So we will divide this 140 bending moments by 10, which is the strip width of the column strip. And then this will give us 14 foot per foot bending moment, because we need per foot bending moment in slabs in order to calculate the spacing of reinforcement. Okay, so this is easy. It can be done like this. 140 is 14, 160. So every bending moment will be divided by 10 for the column strip and by 5 for the middle strip. Okay, in order to obtain bending moments per unit width. Okay. Once these bending moments are obtained per unit width, bending moments are obtained, then the next step will be design, and the design can be done in the usual manner. Before we enter into design phase, we will try to complete analysis for the exterior frame in the east-west direction, and then we will also analyze the east-west interior, north-south interior and exterior frames. And once the analysis for all the frames is completed, then we will design for the bending moments along both the directions. Now for the east-west exterior frame, we will go through this quickly. The east-west exterior frame is calculated. The width of the frame is calculated in this manner: half width of the panel on one side, and then plus half column width, which will be equal to 10, because 20 feet is the panel width. 20 divided by 2 is 10, plus half the column size, which is 14 inch. So half of this will be 7 inch. 7 divided by 12 is 0.58. This will be 10.58 feet, L2. Okay. Now we'll follow the same steps for calculation of the bending moments. Column strip is calculated. Column strip on one side is column strip divided, the panel divided by 4. Panel divided by 4 is 20. 20 divided by 4 is 5 feet. Okay. And half the column is 0.58. So column strip is 5.58. Whole total column strip is 5.58. This is shown by green color. The remaining part is middle strip, which is 10.58 minus 5.58 feet. This will be 5 feet. So once these are calculated, in the next step you can calculate the bending moments following the same procedure that we have used for the calculation of bending moment in the interior frame. The total static bending moment will be WU L2 L square. By this time L2 will change, which is almost half of the value that we have used in the interior frame. Almost half, not exactly half, which is 2. So this will give us a bending moment 285.68 foot kip, which is almost half of the previous value of the interior frame. Then the bending moment will be distributed longitudinally as well as laterally. These are the longitudinal distribution: 0.26 m0, 0.52 m0, 0.7 m0, 0.65, 0.35. Multiply coefficient with the m0 and you will get all these values, 74, 148. And the next step, the lateral distribution, longitudinal distribution and lateral distribution. Lateral distribution to the column strip and middle strip according to these coefficients is done. 1 times m exterior naught, which means this total 74 will go to the column strip. 148 multiplied by 0.6 will go to the column strip. The remaining will go to the middle strip, and so on. So finally, these are the bending moment values: 24, 89, 59, 150, 50, 140, 46. Further, these bending moments will be then divided by the relevant strip width. The column strip width will be used for the column strip bending moments, and the middle strip bending moments will be used for the middle strip. 74 divided by 5.58 and 59 divided by 5. This will give us per unit width bending moments like this. Okay, 13.26, 15.94, 11.87, and so on. These are the final bending moments, and this is a kind of summary on this slide number 50 for the east-west exterior frame. Okay. Next is north-south interior frame. The width of the north-south interior frame is now 25 feet, and the length of every span is 20 feet, because all panels are of same size, 20, 20, 20. Okay, we will follow the same procedure. The only difference is now that the width is 25 feet and the length is 20 feet. And in the previous east-west frames, the width was 20 feet and the length was 25 feet. WU L2 Ln square value will change, because L2 in this case is 25 feet and Ln is 20. L1 is 20 feet. So M0 will change, 421.5 foot kept. M exterior is 0.26 M0, 110.52 M0, 219.7 M0, 295. Okay. Again, I will ask you to calculate these bending moment values for the exterior north-south frame. Again, in 10 minutes. You do this, you calculate the values. Okay. So, and then we will assemble all these values in one slide, in one sheet, and after that we will start designing this slab. Okay. So you calculate now, please you complete these calculations for the north-south interior frame and as well as north-south exterior frame. Okay, please do this. If you have any question, if you want to ask any question now, you can ask your questions now or after you complete your work. It's up to you. You just tell me your name and then ask your question if you want to ask a question. कोई क्वेश्चन आप पूछना चाहते हो तो बस आप सिर्फ अपना नाम बता दें, और फिर आप उसके बाद आप क्वेश्चन अभी करना चाहते हैं या बाद में, तो आप क्वेश्चन कर सकते हैं. ठीक है, अभी आप इसको मुकम्मल करें. नॉर्थ साउथ इंटीरियर फ्रेम के बेंडिंग मोड्स लॉन्गिट्यूडनली तो मालूम हो चुके हैं, लेटरली भी आप लोग मालूम कर लें, और एक ये नॉर्थ साउथ का जो एक्सटीरियर फ्रेम है उसके लिए बेंडिंग मोमेंट मालूम करें, उसके बाद हम इसको डिजाइन भी करते हैं. ठीक है, चलिए आप करें. शाबाश. Okay, so let's now complete this design example. These are the values. You can compare your values with these values for the exterior strip. I hope you have calculated the correct values. Okay, this is the final bending moment values along the east-west direction. Now you should pay attention to the values. First of all, look at the values in the interior frame, which are these values. Okay, values, these values. These are the values in the interior. These are the column strip values and the middle strip values. And then you have exterior frame. Now, if you look at the middle strip values of interior frame and exterior frame, these are these values. Okay. So you have four values here, 10, 9.2 from the exterior frame on one side and the other side, and 9.4. And the other value have been written here, 8.8. This 8.8 should have come here, but for clarity, we have written this value here. So all these four values basically correspond to 1 point here. Okay, and the values are very close to each other. If you look at 10, 9.2, 8.8, 9.4. Obviously, we will use the value of 10 for the calculation of negative bending moment in this middle strip. Okay. Then you have 11.87 and 11.2 because this 11.2 should have also come over here. And these two values, out of these two values, we will be using only one value, 11.87. Similarly, in the middle strip of the interior part, this is 8 and 7.6, we will use 8 value of 8. So for this middle strip, half of which is coming from the exterior frame and half of which is coming from the interior frame, this yellow part is basically the half middle strip from one side and half middle strip from the other side of the frame. We'll be designing this for a 0 bending moment, and then 11.87 positive bending moment, 10 negative bending moment, 8 and 9.2 and so on. Okay. Coming to the column strip of exterior frame. Column strip of exterior frame is these values. These are single values. For every value, negative, positive, negative, these are two values, so we will select the maximum, 26.8, positive and negative values. So we'll select this just like a bending moment for the beam design. Okay, 13.26 is the bending moment per unit strip width. We will multiply this by 12, and by trials we can design for this. Okay, now the column strip of the interior frame. These are the values, 14. And then 16.8, we have 26.3 and 28.3, we'll select 28, and 11.3 and 26. Now, if you compare the values of the interior frame column strip and the exterior frame column strip, they are very close, 14 and 13.25, 15.94 and 16.8. 26.8 and 26.3, 10.75 and 11.3, 15.1 and 26.3, which means 25.1 and 26.3. The values are very close regardless of the size of the frame, because although the size of the exterior frame is small, the width is small, but when we convert these values to per strip width, the width is also small. So the bending moment is small, but the width is small. Therefore, per unit strip width values for the interior column strip and the exterior column strip are almost the same. So along the east-west direction, now we can pick up the values of the bending moment, and we can start our designing along the east-west direction. For example, for the column strip, first of all, let's say we use the value of this how much this value is? 14. 14 foot kip is the value for the column strip in the interior frame. So we will convert this into inch kip, and then we will do trials and find out the reinforcement. It will be placed as top bars in the interior frame column strip. Similarly, for the positive reinforcement in the lower part of the slab, this 16.8 will be used. By hit and trial, you can calculate the reinforcement. 28 for 28 foot kip, again convert this into inch kip, do the trials and find out reinforcement and place this as top bars. Okay, and so on. You can do your design. You can complete design along the east-west direction. Okay, this is the bending moment from the column strip that we were discussing right now. If you look at this 14, 16.8, this is for the middle strip. So once we have the bending moments for the column strip and middle strip, this is just like a beam design. You can do your design very easily by hit and trial method. Okay, there is no need to compare with AS max and minimum, because although we will follow the design procedure of the beam, but this is a slab. So in the slab, AS max and AS minimum need not to be checked, because AS max and AS minimum values will be very, very high, and there is no need to check these values. Minimum is okay. Minimum you will check, I'm sorry, but maximum there is no need. These are the values along the north-south direction. Along the north-south direction, the values will be in the same manner, will be written like this. And then these are interior column strip for the north-south direction, interior middle strip values. Okay, and the next is the design. I strongly recommend that you do this design yourself. You can compare the design that we have finally done for this slab. Okay, you can compare your design values. You can use some other bar instead of number 5. We have used number 5 bar in this design example. And with this we close our today's lecture, and you can practice this design example. You can complete this design with all the analysis being completed. You can do your design now with some different diameter of the bar, and you can come up with questions next time. We will try to complete the remaining part of this lecture in the next lecture. Okay, thank you very much. If there is any question, you can ask your questions. Otherwise, the lecture is over, because this is enough for today. Next time we will try to complete the session 2. Any question?
सर हम सिर्फ इसमें ये इंटीरियर सेक्शन लेंगे ना, और एक्सटीरियर की तो फिर जरूरत नहीं, क्योंकि जब हम इंटीरियर लेंगे तो वही इसमें सेट हो जाएगी ना।
नहीं, हम दोनों के लिए डिजाइन करेंगे ना। डिजाइन तो आप दोनों के लिए करेंगे, लेकिन फाइनली आपको पता चल जाएगा कि इंटीरियर फ्रेम स्पेशली कॉलम स्ट्रिप में जो रिइंफोर्समेंट है तो वो तकरीबन एक्सटीरियर में भी आ जाती है। लेकिन आप देखेंगे सबको, डिजाइन सबके लिए करेंगे, फिर आखिर में ये फैसला आप कर लेंगे। ठीक है, आप देख लें इसको, मेरे डिजाइन को देख लें स्ट्रीट पर, तो आपको अंदाजा हो जाएगा।
ओके सर।
ओके, इफ यू एनी क्वेश्चंस नेक्स्ट टाइम आप इसको कंप्लीट करें तो क्वेश्चंस के साथ आ जाए, इंशाल्लाह फिर हम इसको डिस्कस कर लेंगे। ठीक है, ओके, थैंक यू।
ओके सर, थैंक यू सो मच। अल्लाह हाफिज़।
थैंक यू सर।